Okay, hello everyone. I'm Sukrit Kalra, and today I'll be presenting ERDOS, an open source, dynamic, deadline driven system for autonomous vehicles that is being built inside the RISE Lab. We will be starting off with a quick overview of the project, which will be followed by a mostly asynchronous tutorial. I have my collaborators, Yanel, Peter, and Eyal here, and they're going to be around throughout the session. So please feel free to use either the Zoom chat or the Slack channel to ask questions and interact with us. And to keep things streamlined, I would request that you keep your microphone muted throughout the duration of the talk. As I mentioned in the welcome message on the ERDOS channel, everyone should have received their unique link to the tutorial. If you haven't, please reach out to any of us and we'll get you set up. Okay, let's get started. So let's start with an overview of what an autonomous vehicle pipeline looks like. It starts with a bunch of sensors, cameras, LiDARs, radars, and GPS modules. Usually there are multiple instances of these, and they all run at different frequencies. The data from all of these sensors is communicated to the perception module that is tasked with detection of objects, lanes, traffic lights, and traffic signs in the scene, as shown by the blue block boxes in the image on the right. The bounding boxes for these detected obstacles will then be passed on to an object tracker, which will assign them numerical identifiers in order to track the movement of an agent, such as a car or pedestrian, across the frames. The objects detected by the perception module and the numerical identifiers generated by the object tracking module are then used by the prediction module to initialize the agent's current state in the world and to predict its future trajectories. For example, the blue lines in the image on the right shows the predicted trajectories of the vehicles, and the golden lines, like the one on the top right, show the predicted trajectories of the pedestrian. The planning module then uses these current locations and the predicted trajectories of other vehicles to come up with a plan for the ego vehicle to reach its destination. This involves both a high-level Google Map style route planning that generates coarser-grained waypoints for the autonomous vehicle to follow, and fine-grained path planning that takes these coarser-grained waypoints and generates a short horizon trajectory for the AV to follow. Lastly, the collision avoidance planner seeks to alter the route generated by the path planner in order to prevent collisions with other agents in the scene. The result of all of these planning modules is the green path shown on the image on the right that the eco vehicle follows. This plan that we just come up with is then used by the control module to generate steering and acceleration commands for the underlying machinery with the goal of maximizing comfort and minimizing jerk. So the pipeline that we just discussed and that's shown on the slide is the typical architecture of an AV pipeline being used by almost all of the major vendors that are in business today. However, one key aspect of the pipeline is that it needs to be able to react faster than a typical human would in a similar situation in order to be more responsive than humans and provide a safer ride. While the average human response time is about a second, there is no clear consensus on what the end-to-end response time of this entire pipeline should be. This is fundamentally because the response time required from an AV pipeline is not static and varies both based on both the environment that the vehicle is driving in and its driving speed. For example, driving on a highway is not the same as driving in the city. Driving in the city requires a vehicle to immediately account for the reaction of many pedestrians and vehicles, whereas driving on the highway is easier because of the lack of pedestrians and that most vehicles are far apart and tend to stick to lanes. That's why companies tend to achieve autonomy in highways first than they do in cities. Moreover, the choice of an accurate response time is complicated by the driving speed of the vehicle. The faster a vehicle drives, the faster its reaction time needs to be in order to ensure safety in a similar situation. So this is exemplified by the scenario on the screen where a pedestrian jumps out from behind a parked truck. We have calculated the stopping distance, which is the distance traveled by the vehicle from the moment it sees the pedestrian, and includes the distance traveled during the response time of the pipeline, which is shaded in yellow, and the distance taken by the underlying machinery to come to a halt as soon as the brakes are applied, shaded in blue, also called the braking distance. We see that while a vehicle traveling at 12 meters per second is able to prevent a collision with this pedestrian with a response time of 500 milliseconds, it requires a response time of 200 milliseconds at 14 meters per second in order to come to a halt just before the pedestrian. While picking this appropriate response time for a given situation and driving speed is complicated, the components of an autonomous vehicle pipeline also make it difficult to adhere to the chosen response time. This is because the runtime of the different components, for example, the tracking, prediction, and planning, vary widely and depend on the environment in which the vehicle is driving. For example, the runtime of an object tracker that we discussed before depends on the number of agents in the scene. So, an object tracker will run considerably faster for the image on the top that has just a few pedestrians than the image on the bottom with more pedestrians. Similarly, the runtime of the prediction and planning module also depends on the number of agents present in the scene. To exemplify how runtime can change with the number of agents, we conducted a simple experiment to measure the effect of the number of agents that the number of agents has on the runtime of several object tracking solutions. In our experiment, on the y-axis, we show the runtime, and on the x-axis, the number of tracked agents for three different trackers: sort, deep sort, and the Siamese network. What we see in the figure is that as the number of agents increases, the runtime increases, and implicitly the resources required to track all these agents. This propagates through and through the pipeline, as the pipeline has to predict future trajectories of more agents, and planning components might have to deal with more complex situations. Moreover, unlike typical real-time systems, this response time and runtime estimation is not something we can do just once and expect to use it forever. This is because the components of the AV pipeline are undergoing constant innovation and are being replaced at a breathtaking speed. For example, the five best ranked submissions on this year's Kitty Car Detection Challenge are all from within the last 3 months, and the top ranked submission is 5 times faster than the top ranked from 2019. We cannot expect not to continuously deploy these advancements into vehicles on the road, since they may end up saving lives. These constantly moving parts in all components of the pipeline complicate a static assignment of response times to each of the various modules in the pipeline. Hence, an execution system that underlies an autonomous vehicle pipeline, or any robotics application in general, needs to be able to provide developers with proper tools to be able to handle this uncertainty. Specifically, the system must allow developers to dynamically vary the response time of both the complete pipeline and each of its components. This is required by the vehicle to adapt to changes in the driving conditions and the speed of the vehicle. The system must allow components to swiftly react to any variability in its runtime. This ensures that end-to-end deadlines are met even when the components fail to meet their local deadlines. Finally, the system must allow developers to be able to rapidly innovate on individual components without requiring cascading changes throughout the pipeline, and hence immediately utilize advancements in model accuracies and algorithms to ensure greater safety. However, the current generation of systems underpinning autonomous vehicles, such as ROS and ZeroMQ, and general purpose data flow systems, such as Spark and Flink, fail to meet these requirements since they do not allow developers to define and enforce even static deadlines. While developers can write ad hoc code that utilizes frequency timers to ensure that static deadlines are met, this task becomes complicated when the application requires the ability to dynamically change the deadline and to be able to enforce it across various components. So, to allow developers to be able to effectively program such applications that require a dynamically varying response time, we are building ERDOS, a dynamic deadline-driven distributed system. In a nutshell, ERDOS allows developers to manage time to ensure that deadlines that vary due to the environment and driving speed can be met in the presence of variable runtimes of components. This variability can stem from both the complexity of the environment and the rapidly changing components. Finally, all of our work is open source, and you can use the GitHub link on the screen to see more. In addition to the execution system, we have also built PYLOT, which is a state-of-the-art autonomous vehicle platform with modular components that allow developers to plug and play different implementations of the various components in the pipeline in order to develop and test the effects of new algorithms and models on the driving behavior of a vehicle. Similar to ERDOS, PYLOT is open source and is the only open source autonomous vehicle pipeline that works on the freely available Kalra simulator. To give a high-level overview of the separation between ERDOS and PYLOT, Let's consider the pipeline we discussed earlier. For this pipeline, ERDOS acts as the execution system that lies underneath these modules and enables their execution and the communication of results from one module to another. It does so by modeling the pipeline as a directed graph where each of the components are implemented as operators, and their communication is enabled by streams that carry typed messages. On the other hand, PYLOT provides the actual implementation for the autonomous vehicle pipeline. PYLOT provides different implementations for the object detection module, such as the efficient end family of networks, faster RCNN, and SSD, to allow developers to deploy various modules and benchmark the accuracy of new algorithms and modules compared to what we have. Moreover, this allows PYLOT a choice of modules in order to be able to effectively trade off GPU latency that we show on the x-axis and the accuracy of the detection module shown on the y-axis. Similarly, PYLOT also provides multiple implementations of the planning module so that different algorithms can be used to ensure the maximum accuracy for a given situation. To dive a little deeper into ERDOS's API, each component of the pipeline is implemented as an ERDOS operator. As an example, let's look at the implementation of an object detector inside ERDOS. The detector receives the input and the output streams and registers callbacks on the input stream while providing the output stream to send the computed results to. This callback is invoked upon receipt of a message, and the input stream and the callback can compute results on the incoming message and send the computed results in timestamped messages to other operators via the output stream. ERDOS also requires each operator to signify the completion of output data for each timestamp by sending a special message called a watermark message. To construct the computation graph, ERDOS requires developers to define a driver script. This driver script connects components together by providing the input streams and the operator type to the ERDOS connect method, which returns the output stream. Finally, calling erdos.run validates the graph and executes it. To go into some more detail on how ERDOS allows developers to manage time, let's look at an execution timeline of the pipeline. The data from the camera is fed to the object detection module, and the detected objects get passed to the tracking module along with data from the LiDAR and the radar module. All of this data is timestamped to ensure that each operator works on synchronized data. Timestamps also allow ERDOS to discretize time so that developers can define deadlines at the granularity of each timestamp. Let's look at what happens if a vehicle needs to reduce its end-to-end response time as a reaction to either the environment or the driving speed. To do that, ERDOS requires developers to define a time allocation policy that receives data about the environment, for example, the obstacles, the predicted trajectories, the lanes, and the driving speed of the vehicle, and it then uses this uh, policy to compute both an end-to-end deadline for the pipeline and a per component deadline for each modules of the pipeline. This per component deadline is then communicated to each of the operators, and we assume that operators are well behaved and do their best to achieve the allocated deadline. To do so, they can adapt from many proactive measures, such as shedding load. For example, the detection operator can choose to drop some camera frames instead of wasting resources on frames that are going to be late anyways. It can batch messages, so instead of discarding those messages, the object detector can also choose to wait for more messages in order to batch these detections together. Components can also choose to prune the problem space. For example, the perception module can choose to resize images, change network backbones, use attention, and the prediction, tracking, and planning modules can just reduce the number of agents that they work with in order to focus on the nearby agents. Lastly, components can always choose to scale up and use more resources to complete their tasks on time. For example, a planning module can request for more CPU time and run things in parallel in order to ensure a faster response time. However, as is inevitable, even with the proactive measures, there might be scenarios where a module overruns its allocated time quota. In such scenarios, ERDOS allows developers to define deadline handlers that can interrupt the execution of a module and choose to complete the task using any of the various reactive measures. For example, the deadline handler can choose to output the previous results, tweak previous results. For example, the planning module can just tweak the waypoints that it generates and send them out, or it can choose to run a faster implementation. This brings us to the tutorial, which will allow you to explore both ERDOS and PYLOT and see how proactive measures a component can take to ensure safety. Specifically, the tutorial sets up a scenario where a pedestrian jumps out from behind a parked truck and explores how different configurations are required by a planner to ensure safety across various driving speeds. In conclusion, different environments and varying speeds require an AV to dynamically vary its response time. And moreover, the runtime of these components is not static due to both complexity in the environment and due to the fact that they are being rapidly innovated on. As a result, we have built ERDOS, which is a dynamic deadline-driven data flow system that allows applications to adjust their response time and react to variabilities while meeting their end-to-end deadlines. We've also developed PYLOT, which is a state-of-the-art autonomous vehicle pipeline that allows developers to plug in components and test out their accuracy on a vehicle's driving behavior. And not just that, PYLOT is able to run on a real vehicle. The video on your screen shows PYLOT in action on both a real Lincoln MKZ vehicle and the Kalra simulator. Thanks. Thanks for attending the presentation. I will now be splitting everyone across breakout rooms. Please feel free to discuss the tutorial amongst yourselves or reach out to us if you have any questions or concerns via Slack. We will also be going around the breakout rooms to ensure that things run smoothly. Thanks again.